Hello everyone and welcome to day 16 of the Jamb Physics in 40 Days series. This series is brought to you by Hoya Learn, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you'll be able to get all the necessary skills and tools that will help you ace Jamb Physics. So peradventure you are preparing for the Jamb exams and physics is one of the subjects you have selected, then this video is for you especially. So you do not want to miss any of the videos in this series. So please check out the videos from day 1 up until day 16. Now, the individual videos have been tailored in such a way where we tackle different topics that are in the Jamb Physics curriculum. We give a crash course to what is expected of you for the exams, and then we solve past questions on those topics, while also giving you some tips that will help you solve those questions better and always arrive at the best answer. So please check out the videos. You don't want to miss any one of them. And also don't forget to like and share so that you can also help your friends who are also preparing for the exams. Let us all do well in our exams. So please like and share the videos and also subscribe to the channel, because when you subscribe, you are helping us to be able to make more helpful videos like this. So click the subscribe button and hit the notification bell icon so that you get alerted every time we put out a new content. And also, to practice more, you can download the Exam Fund app. I will add the link to download in the description box of this video. So please click the link and download the app either from the Google Play Store or from the Apple Store, depending on your device. That app is created in such a way that it makes your learning experience fun. You solve questions in different levels and then you get better skills at solving questions faster and better as each of the questions are timed. So please download by clicking the link in the description box. Day 16 of the series is about change of state. Now, if you recall from day 15 where we talked about specific heat capacity, that tells you the amount of heat required to raise the temperature of a substance. Now, when we get to change of state this time, we'll be looking at what we call latent heat, and latent heat can be of either vaporization or fusion. Now, there's a difference there. There's latent heat and there's specific latent heat, which is why we have to look at what Jamb expects of you. Now, before the exam, Jamb expects that every candidate should be able to differentiate between latent heat and specific latent heat, or fusion and vaporization. Now, when we say latent heat, it is the amount of heat that is required to change the state of a substance without any increase in temperature. Now, this is the part that usually confuses students. Always take note of this. When you are working with specific heat capacity or heat capacity, that one focuses on change in temperature. That is heat required to change the temperature of a substance. But latent heat is focusing on the heat required to change the state, either from solid to liquid or liquid to gas, or in the reverse direction, which is from gas to liquid, from liquid to solid, without there being a change in temperature. I believe by now it shouldn't be a confusion to you that when the melting point of ice is at 0 degrees Celsius, it means that you can have water at 0 degrees Celsius just as you can have ice at 0 degrees Celsius. That 0 degrees Celsius is just the partition between ice to water. So there is no change in temperature when it is changing from one state to the other. There's no increase in temperature. It all happens at the same temperature. So that is latent heat. However, specific latent heat, it means the amount of heat required to change the state of a substance when the substance is 1 kilogram. So that is, you are looking at a unit mass of a substance changing state without an increase or decrease in temperature. Now, when it is moving from solid to liquid, for example, ice to water, that is called specific latent heat of fusion, right? And then when it is going from liquid state to vapor, then you are looking at latent heat of vaporization. So that's it about that part. Another thing that they expect from all candidates is that you should be able to differentiate between melting, evaporation, and boiling. Now, melting is when a particular substance changes from solid state to liquid state. However, when you come to evaporation and boiling, the substance is moving from liquid state to gaseous state, but there is a difference. Now, when you look at evaporation, this takes place at a temperature below the boiling point. However, boiling is when it changes to its vapor state or gaseous state at a specific temperature known as the boiling point. Now, there are a number of factors that you have to put into this, and one of them is that for evaporation, for example, it only takes place at the surface, while for boiling, it takes place throughout the entire liquid, which is why you see when something is boiling, it forms bubbles even within the liquid. That is, those molecules within the liquid are changing into vapor even right within the liquid, but evaporation only takes place at the surface. Another difference there is that for evaporation, it requires the heat from the surrounding, whereas for boiling, it requires a specific heat source. There must be heat being provided, whether from an open flame or from a burning of fuel. Something must provide the heat for boiling to occur, while evaporation will just take the heat from the surrounding and use it to change state of the substance. Another thing that you should also put into consideration when you're looking at the difference between evaporation and boiling is the time rate at which this occurs. Now, evaporation is a slow process. It takes a large number of time for a substance to fully evaporate. But for boiling, it takes a shorter time because you are providing the amount of heat required, so it should just happen as fast as possible. Now, these are some of the differences. However, you can get more insight to this by checking out our videos where we discuss latent heat in full detail. So please check it out, and also don't forget to like and share the videos as you do so. Now, another thing that is expected of you is to be able to examine the effect of pressure and dissolved substances on boiling and melting point. Now, when we look at pressure, the more the pressure, the higher the boiling point. That is, when you lower the pressure, boiling point reduces, which is why you see at the top of a mountain, for example, where pressure is lesser, you see that things boil faster at that point. Like, for example, when we know water to usually boil at 100 degrees Celsius, at the top of a mountain, say like the top of Kilimanjaro or Mount Everest, water is going to boil a lot more faster with lesser temperature, sometimes as low as 90 degrees, 70 degrees in some cases, depending on the pressure at that point. So you see, the higher the pressure, the higher the boiling point. The lower the pressure, the lower the boiling point. And the same thing also applies to the melting point. Okay. The only thing here is that the melting point really doesn't really affect it that much. So there's no direct linkage with that. So it only affects it partially, not like in the case of boiling point. That's for pressure. Now, for dissolved substances, when you dissolve substances in a liquid, it is going to raise the boiling point. And the same way it's going to also lower the melting point. So you see, this is why people that are in regions where it snows, for example, always sprinkle salt on the snow that gathers on the floor. This actually lowers the melting point of ice, which will make the ice to melt easily, right? Because it requires a lower temperature to form ice. So you see there, when you add substances to a phase, it will lower the melting point and increase the boiling point. Now, finally, what Jamb expects is that you should be able to use all the informations in what we have stated so far to solve numerical problems, because they will give you problems where you have to calculate. Either you are calculating the latent heat of vaporization, the latent heat of vaporization, latent heat of fusion, and sometimes they would mix specific heat capacity and latent heat to make a question. Say, for example, if you take a substance from its solid state, and then you apply heat until it becomes vapor. You see that it will first gain heat come to its melting point, then gain heat to then change state into liquid state, then gain heat to get to its boiling point before you can then vaporize it. That's a lot of stages in just one question. So you have to understand how this goes and then be able to apply it to solve problems. Now, this is what is expected of you, and we will be solving some questions now where we will apply some of these things. So please pay attention and follow. And if you have any questions at all on what we have solved, or perhaps you come across a question that you don't quite understand how to solve, you can put it in the comment section. We will definitely attend to all of your comments. So if you're ready, let's go solve some past questions on change of states. This question says, an ice cube floats in a glass of water filled to the brim. Now, what happens when the ice melts? Is it A, the water level remains the same? B, there is a drop in the level of the water in the glass due to condensation on its outside? C, the water in the glass overflows? D, the level of the water drops because the melted ice occupies less volume? Or E, none of the above is correct. Now, this is a fusion of change of state and Archimedes principle. Now, we have to recall that the reason why the ice is floating is because it is less dense than water, right? And in this case now, when we consider what we have here, the ice is able to displace its own mass of water. So that means the space that the ice is occupying is the same as the volume of water that makes up that ice. So by the time it melts, it's only going to fill the space that it has displaced, right? So as a result, nothing is going to change in the volume at the end. So the correct answer here will be option A, which says that the water level remains the same. This question from the Jamb 2021 says 0.5 kilograms of water at 10 degrees Celsius is completely converted to ice at 0 degrees Celsius by extracting 88,000 joules of heat from it. Now, if the specific heat capacity of water is 4,200 joules per kilogram per Kelvin, calculate the specific latent heat of fusion of ice. So we see that this 88,000 joules here is a combination of the amount of heat that has to be extracted to first take water from 10 degrees Celsius to 0 degrees Celsius, plus the amount of heat that will now convert it to ice without a change in temperature. Now, should in case you find a question where the ice is now taken to perhaps -4 degrees or -8 degrees, whatever the number is in the negative side, you know you still have to factor in the addition of the amount of heat that will take that ice to a temperature that it is stated there, making the difference as 0 minus the temperature of that ice. So please take note of that in case you see a question like that. But here, we are only going to stop at when it becomes ice at 0 degrees. So let's see what we get. Now, let's start by finding the amount of heat required to take water from 10 degrees to 0 degrees. Extracted from water from 10 degrees Celsius to 0 degrees Celsius. So that would be mc theta. So the mass is 0.5 times the specific capacity is 4,200. Then multiply this by the change in temperature, which is 10. Now, this basically doubles what we have here, because 0.5 times 0.5 is 1 over 2. So 1 over 2 times 4,200 will actually reduce this by half. And that will be 2,100 times 10, and then we have 21,000. So that's for that case. Now, the heat extracted to convert 0 degrees Celsius water to ice. Now remember, without a change in temperature, that is given as H equals mass multiplied by latent heat of fusion rather. Since it's coming to ice, and the mass is 0.5, so 0.5 LF is what we have here. Now the sum of these two is actually what makes 88,000. So we go on to say 88,000 joules equals 21,000 joules plus 0.5 LF. Now if we make this the subject, this is going to give us 88,000 minus 21,000. Now this can be written as LF over 2 equals, what's the difference here? That would be 0, 0, 0, 8 minus 1, 7, 8 minus 2, that's 67. So latent heat of fusion becomes 2 multiplied by 67,000. Now this will give us, now 2 times 0, that's 0, 2 times 0, 0, 2 times 0, 0, 2 times 7, that's 14, 4 carry the 1, 2 times 6 is 12, plus 1, and we have 13. So 134,000 joules per kilogram. That is the latent heat of fusion of ice. So working with this now, since all the answers are in kilojoules, we can then say this is 134.0 kilojoules per kilogram. And that is what we see in option C. Let's calculate the heat energy required to vaporize 50 grams of water, which is initially at 80 degrees Celsius, if the specific capacity of water is given as 4.2 joules per grams per Kelvin, and the specific latent heat of vaporization of water is 2,260 joules per gram. Now, there is a helpful tip that you can use to solve questions like this. You have to consider the unit you are given. Now, you see that the mass of water is given in grams, and the specific capacity of water is given in joules per grams per Kelvin, and the latent heat of vaporization is also in joules per grams. So you can easily work in grams in this case. However, when you are solving a similar kind of question and the units don't match, for example, if this is in grams and what you have here is in joules per kilograms per Kelvin, then you will have to either convert this one into kilogram or you convert this into grams. Vice versa, it will work that way. So they have to be in the same unit for it to work. So let's solve. Now, we see here that the heat energy that will be needed, we first have to raise the temperature of that water from 80 degrees Celsius to its boiling point. And the boiling point of water at atmospheric pressure is 100 degrees Celsius. So if we take that, that means the difference in temperature here is 20 degrees Celsius, right? So that is what we're going to work with. So the total heat required is going to be, first, the heat required to raise the temperature of water to 100 degrees, and that will be the mass, which is 50, multiplied by the specific heat capacity of water, which is 4.2, multiplied by the change in temperature. 100 minus 80 will give us 20. Now, plus, now, the heat required to now convert that water at its boiling point to vapor without changing the temperature. That will be the mass times latent heat of vaporization. And the mass is 50 multiplied by the latent heat of vaporization, which is 2,260. Now let's see what this would give us. The total heat required is therefore, now 50 times 20 is 1,000. 1,000 times 4.2 will give us 4,200. Plus, Now 50 times 2,260. You can do this with your calculator. You get 113,000. So let's add it up. 0 plus 0, 0. 0 plus 0, 0. 2 plus 0, 2. 4 plus 3, that's 7. And then 1, 1. So 117,200 joules. And that is option C. Which of the above combinations are peculiarities of boiling point of a liquid? So let's look at what we have here and then we'll tell which ones are true and which ones aren't. So the first one, we have a liquid boils when the saturated vapor pressure is equal to the external pressure. Now this is correct, which is why whenever you are trying to boil a liquid, for example, all you have to do is just meet up with the external pressure, because that's the point when it's going to boil. So that's why when the pressure is low, you require less heat to boil it, so the temperature would be lesser. Whereas when the pressure is very much high, it requires a whole lot of heat to be able to match that external pressure. So we can say statement 1 is one of the peculiarities of boiling point, so it is correct. Now statement 2 says dissolved substances in pure water leads to an increase in the boiling point. This is also true, as the dissolved substance will stop the molecules of the liquid from being able to arrive at the surface easily. Remember that heat is transferred in liquid by a process called convection, right? Which is the actual movement of the molecules of that substance. So that is, as they gain heat at the bottom where the heat is being applied, they're supposed to go to the surface where the temperature is a bit cooler, right? But because of the dissolved particles in there, they are unable to reach the top faster like that. So that will delay the boiling and increase the boiling point. So 2 is also correct. Now statement 3 says when the external pressure is increased, the boiling point increases. This is also true, yes, because we know that you have to match the external pressure for the liquid to boil. So if you increase the pressure, that means the boiling point will also be increased. So we're also going to mark statement 3 as true. Statement 4 then says dissolved substances in pure water decreases the boiling point. This is the complete inverse of statement 2 rather. So if statement 2 is correct, the inverse is not going to be correct. So statement 4 is wrong. So the only ones that are accepted peculiarities for boiling points of a liquid is statement 1, 2, and 3. So that means the correct one is option A. This is a question from the 2019 UTME that manages to confuse some students. So let's look at it. It says, when water is boiling, now many students actually attribute boiling to increasing temperature, but we really need to understand what boiling means. Now when you hear the word boiling, it means that a liquid is being converted from its liquid state into gaseous state without a change in temperature, right? That is able to gain enough heat, known as latent heat, to completely vaporize it without change in temperature. That's basically what boiling is. Changing from liquid to gas without change in temperature. So you see here that it doesn't get hotter, it does not increase in mass, it does not decrease in mass, but instead changes to steam. So the correct answer is D. During the transformation of matter from solid to liquid state, the heat supplied does not produce a temperature increase because, now to understand this, we have to really differentiate between solids, liquid, and gases at molecular level. Now you see, at the molecular level, what comprises what we know as a solid is tiny particles that are so tightly packed by a strong cohesive force. So the force holding the molecules together is so tight that they form a regular pattern, or we call a regular lattice. That is why you see that solids have a regular shape and a regular volume. On the other hand, when it becomes liquid, the bond that is now holding them is very much weaker than the bond holding them before, right? So this is why you see that the molecules are going to congregate in what we know as clusters, right? They are not so free, but yet they can flow about, right? So that is the difference between a solid and a liquid. When you compare that to a gas, you see that the molecules are completely free this time around, so they can move about as free as they want. So now that we know the difference between solid, liquid and gas, let's see which of these options explains what really happened that makes the solid when they are being changed to liquid not to gain any other increase in their temperature. Now, the first one is saying the heat energy is quickly conducted away. Now, we know this is not true because it continues to gain heat until it is fully converted into liquid. Now, B says that the heat capacity has become very large as the substance melts. Now, the heat capacity of the solid phase of a substance does not change, right? Because the heat capacity is the amount of heat required to raise the temperature. So it does not affect what we are talking about here. And then C says the heat gain is equal to the heat loss. Now, if it is losing the same heat it is gaining, then nothing is going to happen. It won't be converted from solid to liquid at all either. So we are left with D, which says all the heat is used to break the bonds holding the molecules of the solid together. Now, this is true because that bond is so strong. So for it to become liquid, you have to overcome the energy that holds them together. So that is why it's using the heat to break the bond to make it slightly weaker so that it can then flow about freely. So the correct answer here is option D. Calculate the specific latent heat of vaporization of steam if 1.13 times 10 raised to power 6 joules of heat energy is required to convert 15 kilograms of steam to water. If you're yet to be subscribed to the channel, please ensure you do so. When you subscribe, you help us to be able to make more helpful videos like this. So please click the subscribe button and click the notification bell icon so that you get notified every time we put out a new content. And also don't forget to like and share the videos. I want to ensure that this video reach as many people who really need it. So please share the video, and also don't forget that if you have a question at all, if there's anything you'd like us to solve, please put it in the comment section. Perhaps you come across a question and you don't quite understand how to solve it. Put it in the comment section and we will definitely attend to all of your comments. So let's solve the problem that we have here. We see here that the heat energy supplied is 1.13 times 10 raised to power 6 joules, which is basically 1,130,000 joules. And then we also see that the mass is 15 kilograms, right? So we are asked to find the specific latent heat of vaporization. Now, the equation says H equals mass multiplied by latent heat of vaporization. Now, what this implies is that latent heat of vaporization is the heat supplied over the mass. So let's see what that will give us. Now, the heat supplied is 1,130,000 joules divided by the mass, which is 15 kilograms. Now, when you divide this, you will get 75,333.33, and this is joules per kilogram. Now, to put this in standard form, we have to move this decimal point 1, 2, 3, 4 places. So what we have is 7.53 times 10 raised to power 4 joules per kilogram. So when we consider the options now, the correct option is C. Which of the following will increase the boiling point of water? Now, whenever you want to increase the boiling point of water, all you have to do is increase the pressure around it. So anything that increases pressure around it will raise the boiling point. And then, of course, any other thing also that will hinder convection will also raise the boiling point. So let's see which of them. Now, the first statement here says taking it to a high altitude, and we know that the higher you go, the lesser the pressure, right? So if the pressure is reduced in this case, that means boiling point will actually drop, not increase. So this is not true. This will only decrease pressure and decrease the boiling point. Now, statement 2 says dissolving salt into it. And dissolving substance into a liquid will raise the boiling point as it hinders heat transfer by convection. So this will raise the boiling point. Now, the third one says heating it in a sealed flask. Now, when you seal it in a flask, what you have done is to raise the pressure around it. So as a result, it will also increase the boiling point. This is why you see that your pressure cookers are always tightly sealed. That way it raises the pressure around whatever is within the pressure cooker, and so it raises the boiling point. So in this case, this is also true. And then finally, we have increasing the rate of heat supply. Now, this one does not even affect the boiling point at all. The only thing it does, it makes the liquid actually attain the boiling faster. That is, if it was supposed to take 10 minutes before, you may reduce the time to maybe 8 minutes. It does not affect the boiling point because it is still the boiling point that it has to reach before it boils. So this one is also false. So the only true ones we have is statement 2 and 3. And that is what we have in option C. So we go with C. This question says, steam from boiling water causes more damage on the skin than boiling water because, and then it gives us a variety of options to pick from. Now, before we do that, let's really look at what we are considering here. We're considering steam and boiling water. Now, one thing is certain, before you can produce steam, you have to first raise the temperature of water to its boiling point, and then it's at that boiling point to then be converted into steam. But before it gets converted into steam, it's still going to absorb more heat energy to make it break the bonds holding the liquid water together so that it can then become gas, which has free molecules. So let's now look at the options that we have and see which one is accurate. So option A says water has a high specific heat. Now, although this is true, water has a high specific heat, but this does not necessarily explain the severity of the bonds you get from boiling water, because this is only telling us that water will absorb a lot of heat energy before the temperature can then be increased at all. Now, B says steam has latent heat of vaporization. Now, this is right in the sense that whenever you are boiling water, right, it gains heat energy until it gets to its boiling point. Now, at that boiling point, it continues to absorb more heat energy to break the bonds holding the water molecule so that it can then become vapor. So that tells you that steam will have more heat energy compared to water that is just at the boiling point, right? Because to get to the boiling point, you require lesser heat energy than the amount of energy that will take it to become vapor, right? So option B is correct. But let's look at C and D before we then conclude. Now, option C says the steam is at a higher temperature than water. Now, this is completely false because under normal pressure, steam is produced at 100 degrees Celsius, which is the same temperature as boiling water. So they should have the same temperature, not higher. And then finally, we have steam brings heat more easily by convection. Well, this is true that steam brings more heat by convection. However, this does not really explain the severity of the bonds we get from steam, right? So the correct answer in this case will be option B, which tells us that steam has more heat energy due to latent heat of vaporization. A heating coil rated 1000 watts is used to boil off completely 2 kilograms of boiling water. So this implies that the water is already at 100 degrees Celsius, so it should be able to boil it away, convert it to steam without raising the temperature. So the time required to boil the water is therefore, so let's find the time taken. So we apply that the heat supplied equals mass times latent heat of vaporization. Now to find this heat supplied, we're going to apply power times time. So since the power is given, that will be 1000 multiplied by time, we get 1000 T equals, now what we're going to be having on the other side is the mass, which is 2 kg, multiplied by the latent heat of vaporization, which is giving us 2.3 times 10 raised to the power 6. Now we can then say T equals 2 times 2.3 times 10 raised to the power 6 divided by, now 1000 is 10 raised to the power 3, right? So if we solve this, we'll be having 2 times 2.3, that will give us 4.6 times 10. Now 6 minus 3, and that will give us 3. So 4.6 times 10 raised to the power 3, and this would be in seconds. So the correct option therefore is D. This is one of those questions that can create a little bit of confusion if you don't understand the question clearly. Now, it says when left in a freezer, a bottle full of water cracks on freezing into ice because of the... Now, when we consider the options here, we see increase in the volume of the water, contraction of the bottle, expansion of the bottle, decrease in the volume of the water. And then we immediately eliminate C and D, because we know the bottle cannot expand when it is cooling down. It's supposed to contract instead. And then we know that the volume is supposed to increase, so therefore decrease in volume will not cut it. So that leaves us with A and B, where the confusion lies. Now the question is, which one of them actually causes the break of the bottle when it freezes? Now this is it. We know that the volume is definitely going to increase, and we also know that the bottle itself is also going to contract. However, the contraction of the bottle is very minor compared to what you get in the volume. In fact, about 9% of the volume of water increases when it freezes. Now, remember we've talked about it in one of our videos earlier where we said the highest density of water is at 4 degrees Celsius. That tells you that it's cooling into ice, which is between 0 to 4 degrees, is going to expand, and that means the volume is going to increase by at least 9% of its actual volume. So that tells you that we will expect more from the increase in volume than we do from the contraction of the bottle. So the correct one to go with in this question, now take note, even though this is true, the one that actually leads to the breaking of the bottle is the increase in the volume. So we go with option A. This question says, how many grams of water at 17 degrees Celsius must be added to 42 grams of ice at 0 degrees Celsius to melt the ice completely? So we're going to equate the amount of heat gained by ice. Remember, 42 grams of ice at 0 degrees, that will convert it into water. And then we equate that to the amount of heat that needs to be extracted from a 17 degrees Celsius water to bring it to 0 degrees. So this is what we're going to do there. On the left hand side, we're going to do the part for the latent heat of fusion of ice. Now that is mass times the latent heat of fusion. Now if you observe, the mass here is given in 42 grams, while the latent heat of fusion is given in joules per kilogram. So you have to convert this to joules per gram to make it easier to work. So that way we'll have 42 multiplied by, now bringing this to joules per gram means we have to divide it by 1000, which is 10 to the power of 3. That will bring this to 3.4 times 10 raised to the power 2. And 3.4 times 10 raised to the power 2 will give you 340. So write that here. And then we equate it to, now the mass of water, we don't know that yet because that's what we are asked to find. So that will be M multiplied by the specific heat capacity of water. Now if you see the options there, it's also in grams, so, and we are working in grams here. So let's also convert this to joules per grams per Kelvin. So divide this by 1000 and then you have 4.2 times the difference in temperature. So from 17 to 0, that will be 17 minus 0, which gives us 17. So we can easily say M, which is mass, equals 42 times 340, all divided by 4.2 times 17. Now let's break this. This here 1, here it will go 10 times. 17 here 1, 17 here, that will be 20. So what we have is 10 times 20, and this is in grams. So the mass is going to be 200 grams. And that is option A. Now, when you take a look at this question, you see that we are using electrical method here, but we are given resistance and current. Okay, and at the beginning of the video, when I was talking about electrical method of finding the energy that actually is passed into a liquid or a solid to either melt the solid or vaporize the liquid, I did mention that you could have your electrical power as IV, then multiply by T to make it energy. That is, the energy is then IVT, and the same energy can be written as I square RT, and the same energy can then be written as V square over RT. So any of these three equations works, right? So that is what we're going to apply here. So since we're using resistance and current, we're going to be using this particular side of the equation. So let's solve. Now from the question, this current is going to flow for 30 seconds. Right? And we want to evaporate 5 grams of a liquid that is already at its boiling point. So meaning that there will be no change in temperature. We're just going to be using mass multiplied by the latent heat of vaporization. And using that, we're supposed to find the latent heat of vaporization. That is the unknown in this equation. So let's equate the electrical heat energy to the mass multiplied by latent heat of vaporization. So applying this, I square, current is 2, so we would have 2 times 2 multiplied by the resistance, which is 5, multiplied by the time, which is 30 seconds. And this equals the mass, which is 5 grams, multiplied by the latent heat of vaporization. Now, what do we have here? 5 times 30 times 4. That will give us what? So we have 30 times 5 here. This is 0. This is 15. So 150 times 4. And then we have 0. This is 20. 0 to carry the 2. 4 times 1 is 4 plus 2. We have 6. So everything here is 600 equals, now this is 5 LV. So LV, which is the latent heat of vaporization, is therefore 600 divided by 5. Now remember, this is going to be in joules per gram because we are working in grams. So this would then give us, now 5 goes in 60 12 times, so in 0 times. So 120 joules per gram. Now to put in more practice, you can hone your skills by playing the exam phone app. It's a very interesting app that designs your learning experience just like a game-like setting, whereby you get to solve questions at different levels with timing, right? So it also helps you to prepare very well for the Jamb exam, since you have to solve a number of questions in specific time. So you'll find a link to download the app in the description box of this video. So click the link, download the app either from Google Play Store or the Apple Store based on the device that you are using, and then have some fun while you prepare for your exam. And also do not forget to subscribe to our channel. As you subscribe, you are helping us to be able to make more helpful content like this. So we are counting on you. Please subscribe and also like and share the video so that we can reach as many people that really need this content. So please share it amongst your friends. Let it go as wide as possible. Let's reach so many people, please. So don't forget to share. And if you have any question at all, please drop it in the comment section. We are waiting on your comments, and we will definitely attend to every one of your questions that you put in that comment section. Thank you very much for following the series. I'll see you in the next video. Bye.